we're going to look at Minimax, which is an algorithm for figuring out the best way to play a game in an alternating game of two players. We're going to look at tic-tac-toe. So let's just dive into a specific board and a sequence of possible moves. So say we are X and the board is like this and it's X's turn. Well, X has three options. It can go in any of those blank spaces, right? X can go over here, or X can go over here, or X can go over here, right? Once X has gone in one of those three spaces, then it's going to be O's turn. So in the case that X had gone over here, then it will be O's turn, right? And O can go either over here or over here, right? So you can see we're generating a tree of all of the possible moves. Similarly, if X had gone over here, then O can go here or over here. And if X had gone over here, then O could go over here or O could go over here, right? I should point out in this case O had won, so that was a good thing to do over there, and O had won over here. Okay, we've got still a few more possibilities, right? We don't, once O has won, we don't, X can't do anything. But in the case where XO hadn't won, then X goes and, right, goes the one place they can over here, the one place they can over here, the one place it can over here, and the one place it can over here, and this one is actually a winning move. All right, so that's the easy part. We just visually wrote out the tree of all of the possible moves. Now, given this tree, the interesting thing is, can we come up with a mechanism to evaluate each possible move and sort of go reverse up the tree to come back to where we started with, where we are now? Remember, it's X's turn to figure out which is our best move. And generally, what we want to do is assume that we're playing against a good opponent. So when it's the opponent's turn, given the range of options the opponent has, we're going to assume that the opponent is going to make a good choice. And of course, when it's our turn, we think we're going to make a good choice as well. All right, so let's see what this looks like. What we do is we define a function called a position evaluation function. That given a board, it evaluates the quality of the board. And we'll generally give it a -1 if it's really bad, like if it's going to lead to O winning. A 0 if it is medium, it ends in a draw. And a +1 if it's good, if it ends in us winning. Right, I hadn't even noticed, but of course this is really good because X won here, X wins here, so those are +1s. These are both draws, and so those result in 0s. Okay, so that's easy. We start at the bottom, and then we kind of percolate up. And we need to come up with values for every board. Okay, well, in the case when we go up one, if there's only a single descendant, well, then the value of this is going to be the same, right? If X won over here, then this is good for us. No matter what O does, X wins. So this is going to be positive. So for these things, when there's only a single descendant in the tree, we just pass that value up. So this gets a +1 like its child. Similarly, this gets a +1 because that's a winning move, winning because right, it ends up in us winning. These ones were draws, so that is not that great. So that ends up in a 0. And these ones, we saw before that O wins, and so these are both going to get values of -1. All right, how about when we go up again? Now, in this case, what we want to do is, even though the possibility here was that we could win, the reality is that if O had gone over here, O would have won, and we don't like that. And remember what we said before is we're going to assume that the opponent is good. So what we're going to do is percolate up the bad values, right? So this goes up here. Similarly, this goes up here because it's O's turn, and so that's -1. And in this case, the worst thing that can happen is if O is smart and goes over here, which we assume they will, then we'll percolate that value up and we get a 0. Now, when it's X's turn, we get to choose what we want to do. So we're going to pick the maximum value. So we're not going to pick one of these trees that are going to result in a really bad outcome. We're going to pick this, which is better, right? And give us the good outcome. So what we do is we expand the full range of all of the possible moves. We evaluate the leaves at the bottom of the tree, and then we percolate up. And at each level, if it's the opponent's turn, we take the worst possible value, assuming that the opponent's going to be smart. If it's our turn, we take the best possible value of the descendants, assuming that we're going to be smart. And that's how we evaluate our function. And then, of course, when it's actually our turn to move, we will take the board with the highest value. So in this case, what would have happened is we would have gone over here, right? We wouldn't have gone one of the other places. Then it was O's turn, and O would have picked, assuming they were running the same algorithm, O would have gone over here, and then we would have gone over here, resulting in a draw. And the only way we could have won would be is if O had made a mistake, and instead of going over here, O had actually gone over here, but it's unlikely they would have because we would have won the next turn. We did have an option of winning over here, and we could have pursued that had we taken this move instead, but that would have been highly risky, right? Because we know that O has the possibility instead of going over here. And that's Minimax.